Good morning, students. In today's class, we'll just discuss about the band theory of solids. That is Unit 2. Okay. So, uh, we already had the information that what we have completed in the last class. See, in the last class, we just started with the Unit 1, Chapter 1. The Chapter 1 deals with the understanding of the solids classification into two different categories, that is crystalline solids and the non-crystalline solid. So here the crystalline solid is again classified into the two categories, subcategories, that is a single crystal and polycrystal, right? So then we just discuss about the non-crystalline solid, that is also known as amorphous solid. So in detail, we just studied with various examples regarding the single crystal, polycrystal, and the amorphous solid, that is also known as non-crystalline solids, with examples. In the later section, since crystal is a three-dimensional object, so we cannot see it with our naked eye. So we just assume that how the constituent particles inside the crystals are arranged. So in this particular session, we just discuss about the arrangement of the constituent particles by considering important parameters and some basic definitions regarding the uh, arrangement of these constituent particles. So we just discuss about the lattice, crystal lattice or space lattice basis, and the unit cell, and how this particular parameters leads the uh, assumption of the crystal structure, right, in two dimension. So again, in the later section, we discussed about the different crystal systems, right? There are 7 crystal system which is residing on the earth crust. So now we just discuss about this. After the crystal system, we just discuss about the previous lattices, and also we had an information regarding interplanar spacing. So now, since a student should have information up to this, how the structure of the crystal um, is located, and the next one we just discuss about the interplanar spacing, which is in between the two crystal planes, and how this mathematically crystal planes can be located by means of Miller indices. Okay, so now the next part, we just discuss about the X-ray diffraction, that is Bragg's equation, and leading to the different X-ray diffraction methods. So we just discuss out of 3 diffraction methods. We just discussed about the powder method, and with this powder method, what is the aim that that is actually um, we are getting from this powder method? So by means of powder method, you can just determine the form and the size of the crystal. So different properties can be studied by incidenting the X-rays on the crystals. So there are various applications of the X-ray diffraction, and in that applications, right, we just discuss how this can lead to the different what you can say, for an engineering student, what are the basic applications, that is the end of our talk of the first chapter, crystal structure. Then, so this is the ideal case that we have discussed in the chapter 1. In the chapter 2, we discussed that practically there is the constituent particles which are residing inside the crystal. They are not arranged in sequential order, so there are some different defects which are present in the solids. For engineering purpose, we had a classification of the crystal defects, that is imperfections, which is occurring inside the solid when practically viewed, right? So that we discussed that there are different types of defects: zero dimension, that is point defect; one dimension, that is line defect; and two dimension surface defect; and three dimension volume defect. and we have given a due importance to the point defects. And in that point defects, we just discussed about the substitutional defect, interstitial defect, right? And the vacancies, and also we discuss about the electronic defects. So since we are more bothered here in our syllabus about the electronic defects and how these electronic defects can be mathematically verified. So we just discussed about the equilibrium concentration of Schottky and Frenkel defect, which come under the category of the electronic defect, and which is the example of the point defect. So we just had an equilibrium concentration derivation of the Schottky effect, not only in the metals but also in the ionic crystals. And also we just discussed the equilibrium concentration of the Frenkel defect. So with this, we just concluded our unit 1, chapter 2. So here, since a student, engineering student, is having an information regarding the structure of the crystal, that is trying to deal with the different solids classification. So here, since we had a basic idea about the crystal structure, and how this crystal structure gives us the complete information regarding the arrangement of the constituent particles inside the crystal. Here, definitely every solid, if you talk about anything, right, solids, liquids, and gases, it will have some energy, right? So that assumptions of these energy possessed by the solid is given by different scientists. So here in this today's session, we just discussed about the first concept, that is called Drude and Lorentz classical theory, or we just say free electron classical theory, uh, which is residing inside the solid, right? So since we had very clear information regarding the solid which are there inside the crystal, means the exact information regarding the solids. So now what will happen when we just go through the when the electron is moving inside the crystal, that actually we are going to learn in the unit 2, chapter 1. What will happen to the what you can say, the character of the crystal when we incident the electron, or the electron is traveling inside the crystal. So basically, different assumptions which are made by different scientists regarding the character of the crystal when we incident the electron inside the solid. So in the first case, we just discussed about the Drude Lorentz theory, or we just say that the free electron theory. So since this is the basic idea which is given by the different scientists. So here we just had an information regarding the electron, the movement of the electron when it is traveling inside the solid. So particularly we deal with the macroscopic theory. This is Drude and Lorentz is a macroscopic theory in which the electrons move. You can see the electrons is moving freely in the lattice, and which is obeying the classical mechanics. So here the electrons are assumed to be moving in a constant potential. That was the basic assumptions which is made by the classical free electron theory. So we just come to the latest section regarding the quantum theory, brilliance, and so on. So first of all, what is this electron theory? What is the need of studying this electron theory? So here the electron theory explains us the exact structure and the properties of the solid through their electronic structure. So it explains the binding, how the solids is bind, right? How the atoms, molecules, or the ions which are binding the solids, right? So since you know the definition of solid, that the constituent particles inside the solids are closely bound. So here, when I say solids, definitely solids have been classified into metals, non-metals, and semi-metals. That is the behavior of the same solid at different temperatures, which will act as, sometimes it will act as a conductor, insulator, and also the semiconductor. So here we will have very good information regarding the different properties which is exhibited by the solid, right? That may be the electrical, thermal conductivities of the solid, and definitely what are the different types of forces which are acting inside the solid such that the constituent particles are binded inside the solid, right? So, so what is actually the first theory that is put forward by the Drude and Lorentz, that how the movement of how the crystals inside the crystal, how what is happening to the uh, arrangement of these atoms, molecules, or the ions, and also we just discussed about the particularly we discussed about the metals, right? So if the solid is a metal, then how the in the metal, we just say that when I say metal, it is a conductor. How the electron is behaving inside the uh, solid, right? And how what is the character of that particular metal will be changed when the electron is traveling inside the crystal. That basic theory was developed by the Drude and Lorentz, so during 19th century, and it is also known as the Drude and Lorentz, right? You will see this Drude and Lorentz theory. So according to this theory, a metal is consisting of, when I say conductor, right? So conductor is nothing but consist of electrons. What is charge carrier? The conductor is having, that is called the electrons. You can just say the charge carriers is nothing but it is the electrons. And when the Drude and Lorentz assume that the electrons are free to move inside the crystal, how the molecules of a gas is will move in a given container. So here the different assumptions which are made by the classical free electron theory or Drude and Lorentz theory regarding the composition of the constituent particles and also how the electrons moves inside the metal, right? So they assume some important parameters, or we say that is called the postulate of the classical free electron theory. You can see this in all the atoms are composed of the see all the atoms are inside the solid is composed of atoms. Each atom will have nucleus. Definitely atom will have a nucleus at the center around which the electrons are moving. Now this was the assumption which is made by the classical free electron theory, and we are very much aware about this particular assumption, right? The next important postulate that it has been assumed by the classical free electron theory, it says that the electrons are electrons inside the solid will move uh, freely in all the possible directions throughout the volume of the metal. So if there is no electric field, then the electrons move in the random directions, making the collision with each other uh, time to time. And also the positive. And see, we are not assuming the assumptions. Definitely, electrons will electron try to collide with them. But here we are interested in how these electrons are colliding with the positive ions which are inside the metal. So the collision with the positive ions which are fixed in the lattice, we just discussed in the last chapter also, that is unit 1, chapter 1, that there are the atoms are residing, right? So atoms are residing at a particular fixed point, and definitely atom will have a positive charge. So which are fixed in the lattice, and other free electrons, all the collisions are elastic. What is the meaning of this? All the collisions, it may be the positive ions collision. There will be no loss of the energy with respect to the collision of the electrons with the positive ions, right? So this is the case when then there will be no electric field. This you need to understand, that when no electric field, so in the absence of the electric field, right? This is the case which is occurring when the electric field is absent, or we don't apply the electric field. So what will happen when the external electric field is applied? The definitely the electrons are slowly drifting, or we just say that they are crawling towards the positive potential. Definitely the electron and positive potential, the so when the external field is applied, the electrons are slowly crawling or drifting towards the positive potential. Since the electrons are assumed to be we just assume that it is a perfect gas which is obeying. So if it is a perfect gas, so definitely it will obey the kinetic theory of gases. So here uh, we say that the electrons are freely moving. So definitely the electrons will have some velocity also. So what type of how do we can calculate the velocity? By classical free electron metals. Electrons in the metal obey the Maxwell-Boltzmann statistics, right? So we just started with the different assumptions which were made by Drude and Lorentz, that the electrons are freely moving inside the uh, volume of the metal. And when what is happening when the electric field is not applied to the crystal, metallic crystal, so electrons are moving randomly, and definitely they try to collide the positive ions, and when they are colliding with the positive ions, definitely there will be a loss of energy. But here the Drude and Lorentz says that there will be no loss of energy. So what will happen when the external field is applied? So definitely electrons will slowly crawling towards the positive potential. And definitely as I said to you, that the electrons will have, when they are moving freely, they will have some velocity. So they will obey the classical kinetic theory of gases. So now this, what you can say that this is the assumptions which are made by the classical free electron theory, or we say that is Drude and Lorentz, right? With this assumption, what is the, what you can say here, uh, see what are the this is all the assumptions which are made by the class Drude and Lorentz. So what are the different merits and demerits of this classical free electron theory, right? So here you need to understand the, if you can understand uh, 2 to 3 drawbacks, I think that will be enough for you. uh, so if it is possible, you just remember two different important defects, or we say the demerits of the classical free electron theory. We just start with the demerits of this classical free electron theory. See, uh, right? So here, what was the first one that we need to understand here, that the theory is failing to uh, explain how this ferromagnetic superconductivity and photoelectric effect and Compton effect is possible inside the crystal. And also the black body radiation has not been explained clearly regarding this free electron. If we assume, see, sir, we just now we haven't studied about anything about the superconductivity photoelectric effect. So how you can, so that they are the demerit? See, since if you assume some important postulate, definitely you need to get the information regarding this important mechanisms, that is magnetism, superconductivity, photoelectric Compton effect, and also black body radiation, which has not been explained by this classical free electron theory. And also it is a macroscopic theory. So since it is a macroscopic theory, we are actually learning about the constituent particle inside the crystal, which should be studied microscopically. Which is, so now these are two important demerits. There are various demerits, but you need to, if you can just remember this two, that will be definitely worthy for you to reproduce in the examinations, right? So now, what are the important applications of this classical free electron theory? With this assumption, what can be explained about these solids? So actually, it is used to, this classical free electron theory is used to verify the Ohm's law, that is V is equal to IR. The electrical and thermal conductivities of the metals can easily be explained by this theory. And also there is a Weidmann-Franz law, which is derived, right? So which deals with the what you can say, the at a high temperature, what is happening to the metal when it is applied to high temperature. This Weidmann-Franz law, we just say that is called K by rho T is equal to L. So it is used to explain the optical properties of the metal. So different optical properties of the metal has been explained very clearly if you just consider this Drude and Lorentz theory, right? So with this, you can, if you can remember this merits and demerits, two to demerits, I think that will be enough for you. So if it is possible, you can just go for more merits and demerits. But for now, if you can just remember this two, that will be enough for you. So right. So now with this, we just started with the, what you can say, the assumptions which is made by the particular scientist. how the electrons are moving inside the metallic crystal, and what is happening when in the absence of the electric field. If you don't apply any electric field to the crystal, what is the scenario? And if you apply the electric field, what is the scenario? And definitely when you talk about positive and the negative charge, they will be having some forces of attraction, and definitely they will try to collide, right? So that collision also has been explained, right, in this particular theory. So right, with this we can just say that this is the end of the classical free electron theory. So in the next one, we just discuss about the assumptions which is made by the chronic penny scientists. These are the two scientists which has given their own assumption regarding the movement of the electron inside the crystal, in the metallic crystal. See, we are dealing with metals, right? Why? Because of its engineering importance, right? Slowly we just deal with the conductors, and then we'll go for the semiconductors, and at last in this particular chapter we'll deal with the semi conductor, and also we deal with the um, insulator. So how this particular properties will be particular topics will be studied in detail. So for now, we just had an information regarding the classical free electron theory, right? So they have given their own assumption, this Drude and Lorentz, regarding the movement of the electron in the absence of electric field and also in the presence of the electric field. Now, the other assumption which is made by Chronic and Penny, right, how the electron will travel inside the crystal, metallic crystal particularly. So what they say, that we just see this. See, according to Chronic and Penny model, there will be so you can just see the diagram, right? The movement of the electrons will is nothing but we just say array. This is square, right? So they say that these are what square wells. These are what square wells. You can just see they are square wells, right? So here the what you can say, the points which is given here, dimensions is a, 2a, minus a, and minus 2a. What is a here? That is the what you can say a periodicity, periodic lattice, or the character of the crystal, right? That will give us the information that mathematically, that will give us the information regarding the character of the crystal. And you will understand V is the potential. Definitely electron, when electron is moving inside the metallic crystal, it will have a potential. Uh, so if that is denoted by V, and here V naught is the maximum value of the, or you can say the maximum potential of the what you can say, the movement of the electron right inside the crystal. And definitely when we talk about metallic crystal, you'll have a positive ion cores. See, you can just see schematically they are the positive ion cores. And what is W here? This is called the width of the potential barrier. Square well here, say square well, or the width of the potential barrier. So this can be explained mathematically by using the Schrodinger wave equation of the one dimension periodic lattice. I will just show you what is this equation is related. And definitely in the later section, when we move to the next unit, we'll understand what is Schrodinger wave equation, what is actually the meaning of Schrodinger wave equation, and how this Schrodinger wave equation can be mathematically derived, right? So here just Chronic and Penny has taken the help to make their what you can say statements valid by mathematical derivation, right? So by giving some mathematical explanation regarding their assumption that the electron inside the crystal will move in the inside it as a square wells, an array of square wells. So definitely see, whenever in physics you already know that whenever some sentences there's some facts or hypothesis is given, that should be verified mathematically. So regarding this, they have given us the information that see the solution of this equation one. So I will show you what is that equation one also. So that equation one is actually those square psi by x square plus 2m 8 pi square m by h square e minus v into psi is equal to 0. So that is actually the equation one. So according to the Bloch, since it is a second order differential equation, it will have a solution in the format of psi of x is equal to uk of x exponential of ikx. You can just see this particular equation. So definitely you already know that in mathematics, whenever there is a second order differential equation, you need to understand that there may be some solution of this second order or a differential equation. And according to this Bloch, again, we are taking the help of the scientist Bloch. So he has given us the information that the second order differential Schrodinger wave equation is they may have the solution of psi of x is equal to uk of x exponential of ikx, right? So here, what is uk of x? That is called block function. That is uk of x is nothing but we can also write uk of x plus a, where a is the lattice constant of a crystal, which define the character of the crystal, right? So the solution, if you just take the simplification of this particular, we take the what you can say, we go for some differential equations and mathematical manipulations, right? So we just here we are just going for a qualitative treatment. Qualitative treatment means what is actually this equation is employing, what is the main significance of this equation, which is being derived by the considering the solution, second order solution, second order differential equation, and the solution of the second order differential equation. So when you just go for some mathematical calculation, that simplified solution of all the possible energies can be treated in the form of the cos k is equal to p sine alpha a by alpha a plus cos alpha a. So what is actually the meaning of p mathematically? 4 pi square ma v naught omega by h square. And what is alpha here? See, you can see alpha is there. So 2 pi by h under root 2 me 2 me. See, you need to understand this. See, this is a very in detail calculations which has been done mathematically. But since we are not dealing in about any mathematics here, so it is a very trivial issue to solve this particular equation. So what here we are considering here is that we just taking at the end equation of the solution of the second order differential equation, and after different mathematical calculation, we'll obtain this particular solution, right? Cos k is equal to p sin alpha a by alpha a plus cos alpha a. And what is p here? That is called penetrating. I'll show you what is e, p, v naught, p, v naught omega. So definitely, so we need to understand the significance of what. See, whenever some equation is given, so definitely that equation will have some important conclusions, right? So what actually that equation means, right? So that is the reason that we are just writing it cos k is equal to p sin alpha a by alpha a plus cos alpha a. What this implies, right? So p is given and alpha is given. What is e here? See, when I say e, energy is so definitely the movement of the electron is in the form of a wave. You can understand, we have taken the help of Schrodinger wave equation. So what it says, right? So it says that the electron is behaving as a wave. See, in the intermediate, you just studied about also Davis and German experiment in which it has been verified that the electron is behaving as a wave. So what is, if it is behaving as a wave, definitely it also have some energy. So why it has been taking the values, permissible values from -1 to +1, you already know that either it may be sine or cos. You can just see the equation 3, wherein you can just see that the cos and sine values lies in between +1 and -1. So here the energy is having a permissible values of -1 to +1. You can just see the energy is having permissible values from -1 to +1. As V naught as the potential, V naught, I already told you, V naught is the what you can say, the minimum, the value of the potential. Definitely when you talk about the electron, you'll have a potential. So V naught is the potential, and as the V naught is increasing, the width of the barrier, you can, I just told you that square wells is having some dimension, and that dimension, we say that the width of that particular square well, or we say the potential barrier is that way. So what will happen if the potential is increasing? The width of the barrier will definitely decrease, definitely. And what will happen to the product of the potential and the potential barrier? So definitely it will remain constant. One is increasing, another is decreasing. So definitely the two product of two will remain constant. And what is P here? The scattering power of the potential barrier. When I say potential barrier, definitely it will have some scattering power. So, and V naught omega, why we are see, Just now I told you that V naught is increasing and W is omega, or W is decreasing. So what is the importance of studying about V naught omega? So V naught omega will together will give us the information about the strength of that potential barrier. See, P is the scattering power of the potential barrier, how much the potential can be scattered, right? And V naught omega will be the strength of that particular barrier. So here, this was the information which is given by the Chronic and Penny. That's you need to remember. See, this in the two in today's class we just has an assumption of two different assumptions which is made by the four different scientists. First one is Drude and Lorentz, and we had that what actually they assumed that how the metallic crystal is behaving in the absence of the external field and in the presence of the external field, right? So they had some assumptions, based on that assumptions definitely every theory. See, you just studied about the uh, movement of the atoms and so on in the uh, Rutherford theory, and also Bohr's atomic theory, Rutherford atomic theory, Bohr's atomic theory. They have discussed about the atom, and they are having their own views. Here also, they are discussing about the metallic crystal and the movement of the electron inside the crystal. So here also, we just studied about Drude and Lorentz postulates and what are their merits and demerits. Chronic Penny model, they what they were Chronic and Penny want to tell about the movement of the electron, how the electron is moving inside the crystal, and he proved that by means of this expression of cos k is equal to p sin alpha a by alpha a plus cos alpha a, that the electron is behaving in the form of a. You already know the sinusoidal way and the cosine way. So, so what it signifies that the electron is behaving as a wave, and if it is behaving as a wave, definitely some parameters have been assumed here. What is the value of what is actually the meaning of PE, V naught, and V naught omega refers to in this particular equation. So with this, I will take today's class. We'll just end on today's class. In tomorrow's class, we just discuss continue our talk regarding chronic Penny model, and definitely we just deal with the band theory of solid energy bands of the solid. Right. Thank you, everyone. Thank you for your patience. See, so with this, we'll just stop our class.